Welcome all to the PM section of the Science Faculty Postgraduate Research Day. May we now invite our next speaker, Ms. WEI Qixin, Year 4 PhD student in chemistry. Ms. Wei, please.
Okay, good afternoon, dear professors and my fellow. Good afternoon, dear professors and my fellow colleagues. I'm glad I have the chance to share our works here. I'm WEI Qixin from Professor Xiajiang's group in chemistry. And our work will focusing on constructing the catalytic artificial organelle multi-enzyme assembly in E. coli for terpene biosynthesis. In nature, proteins are the most versatile biological building blocks. They often form assembling to form the various sophisticated structures and inhibit the important roles. And their functionality depends on their overall structure, such as the linear, tubular, ring, tubular, and the spherical structure. And the linear structure were the most prevalent morphology, and the ring-shaped structure are involved in the most biological process in living organisms. And also the tubular and the spherical structure provide the spatial control to the biological process and also protect the compound from environment. And inspired by nature, many synthetic protein assembly were developed in order to create the artificial structure with the customized characteristic. And in the synthetic multi-enzyme complex, they can isolate the toxic intermediate, increase the efficiency of the intermediate transfer, minimize the metabolic crosstalk, and also improve the catalytic yield. Compared with other assembling methods, protein assemblies are genetically encodable. Therefore, they are better mimic the nature and easily transit to the biosynthetic pathway. And moreover, there was sufficient robust for the industrial process. And several achievements were successfully applied in the multi-assemblings. And in vitro, our groupmate, Dr. Liu Zhenjun, utilized the elastin-like polypeptide to construct the cyclic scaffold and the cross-link scaffold to assembling the monoclonal biosynthetic pathway enzymes. And another groupmate, Dr. Liu Miao, used the phase separation and found that it can significantly accelerate the efficiency of the multi-enzyme biocatalysis. Multi-enzyme assembly were also successfully applied in vivo. And enzymes were assembling through the scaffold through a docking cohesion interaction and like the cellulosome-like monomachinery and make a marked increase in the catalytic efficiency compared with the mixture of the three enzymes. And also, multi-protein domain can also mediate the assembling of the first three enzymes in melanolic biosynthetic pathway, and a fine control of the metabolic flux and the improvement of the product titer were achieved. These preliminary results set the stage for us to construct the more sophisticated multi-enzyme assembly and construct these synthetic organelles in the bacterial cell for biosynthesis. And in our group, we focus on biosynthesizing the terpene products since they attract more and more attention from the world because of their benefits towards health. And we show the biosynthetic pathway here, and the 5 carbon molecule, IPP and DMAPP, can be generated from the MEV pathway, which is originated from bacterial cell, and also the heterogeneous MVA pathway. And by coupled with the downstream enzymes, different products can be gained. And we focus on the farnesene and biofuel precursor, the amorphodiene, the precursor of anti-malaria drug, and also the beta-carotenoids, the strong antioxidant. And generally speaking, we construct 4 different complexes from the simply scaffold-free modular to the most complicated one, the membrane-bound protein scaffolds. And we will introduce to you one by one. The first one is to assembling the terpene enzymes on the scaffold-free modular. And in this part, we apply the peptide-peptide interaction and called R1AD and R1DD. And the R1AD will bind to R1DD in 1 to 2 stoichiometry because R1DD exists as dimer. And their high affinity, high specificity, and the relatively small size make them ideal to be served as the protein tag. And we showcase the multi-enzyme assembling in membrane biosynthetic pathway in vitro as the first step. And two enzymes in this pathway called MAN-D and MAN-H were assembling in this part. And the blue label here is shown as represent the MAN-D, and the orange ring here represent the MAN-H. And by fuse the R1AD and R1DD to these two enzymes, that under the native condition, the MAN-D and MAN-H can form the higher order structure mediated by the R1AD and R1DD interaction we described, and also the multimerization state of MAN-D. And we designed three different complexes in this part, and each with 4 MAN-D as a core, it is a tetramer, and also surrounding it we designed 2, 8, and 16 copies of MAN-H. And all these three protein complexes show in the size of 11 to 20 nanometers under the TEM microscopy. And we also evaluated the catalytic efficiency of those enzyme complexes, where show the overall catalytic efficiency were increased by those enzymes. And having this successful preliminary result, we then applied the same assembling strategy to the bacterial cell and mainly target for the lycopene production. And we reasoned that the assembling of IDI and CRTE will directly channel IPP and DMAPP to GGPP synthesis to streamline the beta-carotenoid biosynthesis. And by fuse the R1AD and R1DD to IDI and CRTE respectively, the enzyme complex can be formed. And surprisingly, we found that most of the IDI protein relocated to the plasma membrane with CRTE upon assembling. And this nanomachinery can also enhance the protection of carotenoid fermentation, both in bacterial culture and the yeast culture. This will unveil a new strategy for us to regulate the metabolic flux and encourage us to move forward to install such metabolic node for the biosynthesis for generation the final product. And then the next one, we assembling the terpene enzymes on covalent scaffolds. And similar assembling strategy were applied in this part, but we choose a site-specific covalent interaction here. We engineer and split the cohesion protein into two parts, one containing the lysine residue and the other one containing the aspartic acid. And these two partners can spontaneously react to form the isopeptide linkage. And high specificity, the high motility, and the fully compatible with the biological system were the reason that we use them as the protein tags. And fuse the related enzymes with the catcher and the PEG part and the tag part respectively through the flexible linker, and then co-express those enzymes in the bacterial cells so that the covalent link enzyme complex can be formed. We specifically to assembling the 3 sequential enzymes in malonate biosynthetic pathway for the lycopene biosynthesis. As we described, the spike tag and the capture tag were fused to the enzymes at the C-terminal based on their crystal structure to avoid the disruption of the catalytic activity. And different copies of spike tag and SUTNet were designed here to construct different complexes. And this complex inhibit as the hollow interior space and have the uniform thickness and shapes under the TEM image. And this catalytic nanomachinery produced 5-fold increase of lycopene production and 2-fold increase in ester sensing production. This will further deepen our understanding on how complexity of the enzyme form inside the bacterial cell and make us move forward to construct the most and the more complicated enzyme complex in the bacterial cell. And that is to assembling the enzymes on the membrane-free protein scaffolds. And at this part, we assembling the amorphodiene biosynthetic pathway. And in this complex, we can notice that 3 important gradients were included: the protein scaffolds, the tag enzymes, and also the interaction pairs. And in this part, we choose the tobaccovirus type, and it consists of the single co-protein. And also, we use the linker module we described before. And by fuse the single co-protein with the tag part and the enzyme with the capture part, we can form the enzyme complex as we designed. And for our first step, we use the fluorescent protein to visualize the formation of the to confirm the formation of our enzyme complex. And the significant decrease of the CFP lifetime indicated the occurrence of threat and also the formation of our enzyme complex. And then we assembling the enzymes for amorphodiene biosynthesis. And we found that it is interesting to notice that only the strain we have engineered, the one we formed the complex, show the production of amorphodiene. And this work is the first time to propose a switch-on mechanism for biosynthesis in bacterial. And then we move for the most complicated multi-enzyme complex, that is to assembling the enzymes on the membrane brown protein scaffold. It is much more like the organelle in the bacterial cell since it have the membrane. And then in this assembling strategy, we use the protein scaffold called caviorna, and it is consists from the by expressing the critical and small protein called cavionyl 1, and which has the transmembrane domain and also the C-terminal and N-terminal exposed to the cytoplasmic part. And by inserting into the phospholipid bilayer, the cavionyl 1 can assembling into the vesicle as we shown here. And we first non-covalently assembling two enzymes in the biosynthetic pathway to see the catalytic ability of this enzyme complex. And in vitro, by mixing the purified enzymes, the complex can spontaneously formed, and it showed a higher catalytic efficiency than the untagged enzyme and the free enzyme, which means the enzyme are in free floating status. And we also applied this to see whether it can make the difference in the bacterial cell, and the consistent result we got from this part, and only the strain with the complex can show the higher generation of the final product. To develop it as the general strategy for the enzyme assembly, we next use the covalent assembling. And 3 different complexes were built in this part, but we can show that all of the experimental strains show the higher final product generation than the control strain, which means that our complex may increase the final product generation. And we also purified the complex from the third production strain, and it exists as the 20 nanometers vesicles, and it still maintains the capability to convert IPP into farnesene. So this is indicating that the difference of the experimental strain is indeed influenced by our enzyme complex, and the enzyme complex improve the farnesene production. And in conclusion, we construct 4 different complexes in this work, and for the biosynthesis of carotenoid, amorphodiene, and farnesene. And our work made a step forward to the synthetic nanomachinery with catalytic capability to convert the simple molecule to the complex one, and also unveil a new strategy to the enzyme to regulate the metabolic flux and advance the terpene biosynthesis, and also inspire the development of the synthetic organelle for a broader use in synthetic and chemical biology. And this is the end of our, and last but not least, I want to show my sincere thanks to my supervisor, Professor Xia Jiang, and all my lab mates in our SSB 202 and 204, and the financial support from CUHK and RGC. And thank you for your attention.
Thank you, Ms. Wei. Thank you very much. All right, questions are welcome. All right, thank you, Professor Song.
Thank you for very interesting work. I actually am amazed by this beautiful assembly that you can make. I was wondering that with the terpene-based this multi-enzyme assemblies, one example you said is there are multiple functions that they can do. Can you explain how this type of terpene enzyme can actually insulate the toxic substances?
We didn't figure out that it's indeed because many papers describe that there is a substrate channel effect in the protein complex because they can cluster the enzymatic sites in a closer proximity, so that the substrate can channel from one active site of the enzyme to another one, and then it can decrease the amount of the toxic intermediate. For example, here IPP and DMAPP is toxic to the bacterial cell. So when you lower the toxicity, so the bacterial cell can grow better, and then it can move forward to generate more product.
I see. When you actually fix these terpene enzymes onto the covalent scaffold, does that mean that the double bond on the terpene is going to open up to bond to the covalent network?
No, covalently is just means that the capture part, the tag will fuse to the different enzymes, especially one fuse to the first enzyme and the other one fuse to the other enzyme. And covalent interaction just between these two enzymes and not for the substrate.
You do not actually create a bonding between
Yes.
the enzyme. Huh?
Yes.
Okay. Thank you.
Thank you, Professor Song. Is there any question from the audience? You may enter your question in the chat room.
If I may, I do have another question.
Okay.
Thank you. I think you showed the example of assembly ABC that become increasingly more complex, but actually still regular in terms of structure. I was wondering, in reality, when you actually synthesize this, do you start with assembly A and then build up to assembly B and then further functionalize it to assembly C? Is that how this works? You have an earlier slide to show the structure of assembly ABC.
Assembling ABC. You mean this one? ABC.
Yes. So you can see the structure appear to be increasingly more complex, but still very regular. So is that how you build up the assembly?
Yeah, actually, and this is just the cartoon illustration of how this enzyme complex form, but it is not the actual structure of this complex, which is a theoretically, because it is a non-covalent interaction, although it's high affinity, and actually, I think it's not all the enzyme will bind to the text. So just is a design, a theoretical amount that because RNAD and RNDD will bind into 1 to 2 stoichiometry. So by modifying the RNAD's copies, we can assembling different enzymes numbers and the surroundings.
And then the enzyme structure chemically stay intact.
Yes.
Okay. Thank you.
Thank you, Professor Song. We have a question in the chat room.
I can see here. Okay.
So you can
refer.
So the question is, does the size of the enzymes influence the binding of RIDD and RIAD? And does it have the same function to fuse some substances to the N terminal or C terminal of the enzyme? Thank you.
Yeah, actually, we choose, I first answered the first question, the size of the enzyme will influence the binding of RNDD and RAD. And as we haven't showed the result there, we did the in vitro experiment and to visualize the assembling between these two partners, and it is assembling efficiency is relatively high. So maybe you have the very small interaction influence on their binding, but I don't think it have the strong influence to influence the affinity between the RNAD and RNDD based on our result. But I haven't showed the results here. And it is the same to the second question, whether it will, the spike and spike capture fuse to the N terminal and C terminal of the enzyme will influence this. And actually at this part, the tag part or the capture part will fuse to the C terminals of the enzyme based on its crystal structure to avoid those questions, to avoid those problems.
So I think it's time to for the next speaker, and thank you, Ms. Wei, again.
Okay, thank you.
Thank you very much. So may we welcome our next speaker, Ms. Yang Jingting, Year 5 PhD student in chemistry. Ms. Yang, please.
Good afternoon, dear professors and my fellow colleagues. Today, I'm glad to be here to give a presentation on the Postgraduate Research Day. My name is Yang Jingting, and my supervisor is Professor Xie Zhouwei. We are from Department of Chemistry. Today, I'm glad to share my work titled Synthesis and Reactivity of Tantalum Alkyne Complexes, supported by linked carbonyl cyclopentadienyl ligand. Here is the outline of my presentation. For introduction, as we know, alkynes are organic molecules containing carbon-carbon triple bonds. Alkynes are versatile ligand in organometallic chemistry with various binding modes and electron counts. The bonding interaction between an alkyne ligand and a transition metal center can be described as a donor acceptor form or metallocycle form. Transition metal alkyne complexes are important intermediate in many catalytic transformations. For example, the well-known azide alkyne and cycloaddition reaction widely used in click chemistry, and alkyne trimerization to give benzene derivatives, Poisson-Count reaction to get cyclopentadienyl, and acetylene polymerization to give polyacetylene. Other hydrogenation, hydrosylation, and catalytic process involve the existence of alkyne complexes. In addition, transition metal pi-alkyne complexes are starting material to construct many of the beautiful metallocycles with unusual structures. And I studied the graphite transition metals. The graphite metal, vanadium, niobium, and tantalum, various metal alkyne complexes has been synthesized using different supporting ligand from the simplest chloro, oxo, amido, to cyclopentadienyl and TP and multi-dentate ligand. However, the reactivity of these graphite alkyne complexes are less studied comparing with group 4 and late transition metal alkyne chemistry. And the synthesis of group 5 alkyne complexes usually involve a low valent metal center in which strong reductants are required. We can see in the picture the reduction of metal halide to give in transient low valent metal center and bind to an incoming alkyne ligand to form alkyne complex. The reduction must be performed in situ, since non-D0 or early transition metal complex are not as accessible as the late transition metals. And the reduction they are usually magnesium and sodium or sodium amalgam. And we use carborane-based ligand to synthesize the graphite alkyne complex, since it is easy to prepare, and the carbonyl is a strong sigma donor and weak pi A donor. In addition, bulky substituents can protect the metal center, and we have successfully employed this carbonyl ligand to organoresin chemistry and study its reaction with alkynes and dihydrogen. And to be the starting point of our project, our group has successfully synthesized the tantalum trialkyl supported by this linked carbonyl cyclopentadienyl ligand. And our research objectives are to develop a new synthetic method for tantalum alkyne complex based on linked cyclopentadienyl-Carboranyl ligand, and to investigate the reactivity of tantalum alkyne complex toward unsaturated molecules, and to understand the bonding and the reaction mechanisms. And inspired by the literature reported method, we found that reductive elimination of group 5A metal polyhydride could offer a low-valent metal center to bind to the incoming acetylene ligand to form alkyne complex, as reported by Hebrich and CUHK. And to initiate our study, we performed the reaction of tantalum trialkyl with p-toluacetylene under the dihydrogen atmosphere, and the resultant alkyne complex could be isolated in very high yield. And we are lucky to got the crystal structure of 2A. Here is the diamond. Here is the crystal structure of 2A. We could see a perpendicular alkyne ligand to the cyclopentadienyl ring, and the benzene ring is coplanar with the NCC-E3 membered ring. And the coordinated alkyne has a CC bond as 1.321 angstrom, which is better described as a carbon-carbon double bond rather than a triple bond. The much elongation of the CC triple bond indicate a strong metal alkyne interaction, and the low field carbon NMR of coordinated carbon indicates the alkyne donates 4 electrons to the metal, and this method can be extended to different acetylene derivatives from terminal O to internal, and with different substituents from aryl to silyl and alkyl. And the yields are good. And here, four of the substrate have got a X-ray crystal O structure and are combined there. We could see in this structure, the alkyne and CC triple bond have also all been elongated to a CC double bond length. And it is well documented that 4-electron alkyne complex can undergo a nucleophilic attack to form an eta-2 vinyl complex or a metallocyclopropene, which is well studied in group 6 metal chemistry. However, group 5 metal eta-2 vinyl complexes are unknown. And in our system, we found that 2A could react with a bidentate phosphine ligand, DMPE, to form a chelated complex of eta-2 vinyl. And, and the complexation reduce the CC bond order and this tantalum carbon bond order, but shorten the tantalum, this tantalum carbon bond distance to a short bond distance, and the low field carbon NMR signal indicate a carbenoid character of this carbon. And when we are trying to synthesize the TMS acetylene complex using the hydrogenation procedure, and we found a non-planar 5-membered metallocycle was synthesized, and the low field, the carbon NMR of this carbon indicates a carbonyl character. This reaction is occurred through the following mechanism. And however, the reaction mentioned before is only occur on TMS acetylene, so we need to find a better substrate, and we found the reaction of carbon monoxide got a 5-membered non-planar tantalum. However, coordination of DMPE could planarize this non-planar metal cycle, and we have got the crystal structure of them. This coupling reaction also proceed well on internal alkyne complexes. And here is a structure of a planar 6-electron tantalum. As the isoelectric analog of carbon monoxide, the alkyne complex could react with isocyanate to form the eta-2 amino acyl complex, and the following in heating of this complex got a 6-electron tantalum pyro, which is non-planar. And here is a crystal structure of the amino acyl complex, like a butterfly of this 2-3-member ring. And this is a non-planar 5-membered metal cycle. And now we have 3 types of 5-membered non-planar metal cycle, from carbon substituent to nitrogen and oxygen. And we could find the trend of shortened carbon alpha bond length and C-beta, but the C-alpha, C-beta bond length have been elongated. And in conclusion, a series of tantalum alkyne complexes have been synthesized, and this tantalum alkyne complex exhibit reactivity toward unsaturated molecules to form CC coupling product, and a series of metal cycles were obtained. Finally, I would like to give thanks to my professor, Professor Xie and Dr. Lu, for their kind help and guidance. Thank my lab mates in Rong Science Building for their help and discussion. Thank our technician, Bella, Sarah, and Dr. Ng for technical support, and Hong Kong RGC and Hong Kong PFS for financial support. And thank you all for your audience.
Thank you, Ms. Yang. Thank you very much. Question and welcome. Any questions from the audience? Thank you, Professor Song.
This is a very interesting work, so thank you for the presentation. I wonder, when you do the synthesis, and obviously you're trying to synthesize the tantalum complex,
Yes.
using the carborane will probably impact both electronic property of tantalum and also the geometric, the steric access of the tantalum metal center, right? It will probably impact this on 2 sides. One is electronical, another is steric.
Yes.
And then for the steric factor part, if the side of the carborane changes, can you still, well, I didn't know that whether you use a different carborane or just one type of carborane as your ligand.
Oh.
The cyclopentadienyl-Carboranyl, right?
Yes.
You're using it. If you change the size of the carborane.
Change the size of carborane.
Right.
Oh, that will be very interesting. We believe if we change the size of a carborane, let's go to the slide.
Yeah. I suppose there are 2 factors on that particular part. You either change the size of a carborane or add alkyl group to the cyclopentadienyl. Both will serve to change the electron density or electron transfer from the ligand back into the metal center.
Yes.
Have you tried that?
Actually, I didn't try to modify the ligand.
Okay.
But I think that will be very interesting.
Yeah. Will this tantalum alkene complex, will this be used as a catalyst or this used as a agent itself? What do you use this for? You synthesize this alkene complex with tantalum. What will this be used for?
To date, our alkyne complex can be used as an agent for CC coupling, and as we mentioned in this slide, but not a catalyst.
Okay, for different type of CC coupling, right?
Yes.
And so I think for that, potentially both the electronic factor and the spatial factor or the steric factor will come into play, or both may have some impact. Well, that's for when you make use of this tantalum alkene complex to actually do the CC coupling, but you are not doing that yet, right?
CC coupling, stoichiometric CC coupling has been achieved, but not catalytic.
It's not a catalyst, or it's used as a catalyst?
It's not a catalyst.
Not a catalyst. It's a stoichiometric agent for CC coupling.
Yes.
Okay. Okay. Yeah, that's clear now. Thank you.
Thank you, Professor Song.